Hello everyone, my name is Shanmuga. Today I'm going to share my research findings in this presentation. This is a recent study developed on subatomic particle simulations and the development of its potentials in atomic scale. As you can see here, this is the image of a subatomic particle simulations of a carbon atom which has 6 electrons orbiting revolving around the nucleus, which is here in the center. You can see this is a classical approach, not a quantum simulation. This is a classical simulations. This is a molecular dynamics algorithm applied on subatomic particles. This study got published in Innovative Journal of Applied Science in the journal. And if anybody is interested, they can go through the full paper. And it has a this study has a preprint also in preprint.org, and here is the link. I shared this link in the description. Anybody is interested, then go through the paper. And okay, let's go into the session. So this research study is a new approach, new in discovery of implementing subatomic particle simulations, where electrons and protons and neutrons, all the three subatomic particles, are placed in the simulation box, and it ran for few time steps or few cycles in Monte Carlo simulations, in case of Monte Carlo simulations, and see how the electrons and protons and neutrons behave, whether the atom formation is happening or there. We applied the Coulomb potentials also, and we have developed a new potentials in order to have a stable atom. So yeah, okay, let's go into the session. So before going to the session, let's have a presentation overview. First we'll have an introduction for the general audience. I'll introduce a few topics of molecular dynamics, Monte Carlo simulations, how it is implemented, and few introduction about the classical approach and quantum approaches. Then we'll have a findings of subatomic particle simulations. First we'll go through the molecular dynamics approach, algorithm implemented on subatomic particles for a hydrogen atom, a carbon atom, uranium atom, and also we implemented on oxygen molecule. We place two oxygen side by side, and the electrons are revolving around each oxygen atom. When it is close by, the valence electrons are shared between the oxygen atoms, and we can see the trajectories of the electrons similar to the carbon atom we see in the previous slide. And then we'll have a subatomic particle simulations of Monte Carlo algorithm. Instead of time steps, we'll have a Monte Carlo random moves, a movement of random of electrons and protons and neutrons in the simulation box, and see how the atom formation and how the electrons are distributed around the nucleus, and we'll see the analysis of it. And finally, I made an attempt to have a, so all this molecular dynamics implementation and Monte Carlo simulation implementations are particle nature, classical approach. There is no wave representation. So I made an attempt of implementing pilot wave theory, of which the wave particle moves according to the interference pattern between the waves of protons, electrons, and neutrons. So that we'll see in the end, and then we'll conclude the session. Okay, let's go into the introduction. So the classical approach on atomic models, or the electrons distribution around the nucleus, had a halt in around the year 1930 because of the development of quantum approaches, quantum theories. So yeah, at the start of 1900s, both quantum and classical approaches are there, and scientists are very eager to investigate how the electrons are distributed around the nucleus, or how the atomic models emerged from this. In 1920, Bohr atomic model came up, supporting quantum simulations, quantum approaches. Heisenberg uncertainty principle and Schrodinger wave mechanics came out. and this favors the approach of quantum perspective. Okay, so and then later the development of quantum field theory happened in 1930s, and the people started to explore quantum perspective of the atomic models and how the electrons are distributed around the nucleus, and all the theories came up, and all the models are all in the quantum perspective. And the thing is, around 1930s there is a classical approach has been halt happened, and because of not enough evidences are there for the classical classical approach for the electrons and protons and neutrons in an atom in atomic scale. So we are here now in 2025. Now after that, many particle systems has came out in quantum perspective, and solid systems has came out. So now we are at the stage of developing the quantum computers, quantum computing, quantum communications. Also recent developments have taken place in the year 2025. But what happened is classical approaches gotten stopped here, and humanity has stopped around at the year 1930. So this study, which got recently published in the journal, it explores this classical approach. Okay, so first we implemented Coulomb potentials. We performed molecular dynamic simulations of placing nucleus at center, and the electrons are distributed around the nucleus, and see how the electrons behave. So the Coulomb potentials doesn't give enough performance, satisfactory performance, because it is not stable. Atom is not stable. All the electrons are attracted towards the nucleus, because protons and electrons are attracted towards each other. So we'll see. So that then we developed a new potential, new approach, new perspective for the subatomic interactions, subatomic particles, so that we can have a stable atom, stable electronic configuration around the nucleus of an atom, stable atom, in a simulation for both molecular dynamic simulation and Monte Carlo simulations. Okay, so for the general audience, let me give a brief introduction on how molecular dynamics algorithm approach is there, how it is applied on atoms. And now in this study we'll apply on subatomic particles also, and also I will explain the Monte Carlo simulations. Okay, so molecular dynamics is very simple if you understand the algorithm of it. So initially we'll have a simulation box. We'll have atoms, say for example argon or any molecules distributed in the simulation box, randomly distributed. This is the initial configuration we'll start with at the start. So what we'll do is we'll calculate forces acting on each atom, on each atom or each molecule, and then we'll calculate the based on the force field, we'll calculate the force acting on the atom for a atomic simulation, and then based on the force acting on it, we'll calculate the velocity of an atom based on Newton laws, by applying Newton laws of motion, and based on the velocity for the next time step, for the next time interval, we can know the exact position of what will be the exact position of each individual atom for the next time step. Okay, so we'll move the atom, so that gives a new configuration. So we'll collect that configuration, and then we'll make another time step, we'll move forward with time, and then we'll calculate again for the force acting for the new position. This time the position of atoms are different, and the forces acting on it are also different. So for the like that, we'll calculate the velocity, and we move again. We'll collect the configuration, and means we'll collect the atomic configuration, system configuration at this time. So we'll repeat it for several thousands of time steps. So what happens at the end of the simulation, we'll have n time steps, we'll have different atomic configurations. So we'll get the properties of it. So now we have the movements of atoms in the simulation box, and we can calculate the properties like temperature, pressure, density, volume of the system, and so on, velocities, potential energy, kinetic energy of the atoms, and assembly, atomic assemblies of the system within the molecules, and all those stuff we can calculate from these configurations. So this is how the molecular dynamics works. We'll start with the initial configuration based on force acting on it, on the force field. This is based on the force field. We can calculate the force acting on the atoms, and we'll collect all the configurations. So now, this is how the molecular dynamics algorithm works for all the atomic and molecular systems so far. And now we implement this algorithm for an atom, single atom within the atom. So what we do, we start with the initial configuration. We'll place a nucleus at the center, and we'll randomly distribute the electrons around the nucleus, and we'll calculate the force based on the force field using Coulomb potential or the new potential we developed here. And we'll calculate the velocity, we'll move the atom, and we'll collect the configurations. So we'll have n time steps, we have n configurations, and we'll calculate the properties based on that, like radius of the atom, energies of electrons on it, potential energy, kinetic energy, like those properties you can calculate. So this is how molecular dynamics works. And now let's move to Monte Carlo simulations. This is also have the same algorithm. The only thing here is we'll start with the initial configuration. Instead of calculating the force, we'll move the atom. We'll move all the atoms in the simulation box randomly. Each one atom by atom will move randomly. Instead of calculating the force, we'll calculate the potential of the system, potential energy of the system, by moving one atom at a time. And based on that potential, this is potential also we'll calculate based on the force field. So in molecular dynamics also we'll calculate the force. In here we calculate the potential based on the force field of the atoms. Force field is nothing but how the force is acting, potential or force are acting on the each atom based on the environment, surroundings of the atoms. Okay, so then based on the acceptance criteria, based on the probability, this random move, whether it is highly probable state or not, we'll calculate, and then we'll accept the move or reject the move. If it is accepted or rejected, we'll collect the properties. Accepting moves, we'll collect the properties. We collect the configurations, and then we'll move again. We'll come to next atom. So like that, we'll have n cycles. So for cycle 1, we'll have all the atoms will be moved randomly, and the potential is calculated, and the random move is accepted or not based on the acceptance criteria, and then we'll collect the configuration. So like that, we'll have n cycles of Monte Carlo cycle, will have n configurations. Here also we'll calculate the properties based on the collection of the configurations we collected. So both are having the same algorithm. Only thing is, based on Newton's laws of motion, we'll calculate the velocity and we move the atom. Whereas in Monte Carlo simulation, we'll move randomly and then we'll calculate the potential and whether the move is accepted or not based on the acceptance criteria, and then we'll move forward. And one more difference is, in molecular dynamics, we'll have time steps. Okay, at each time step 1, time step 2, 3, 4, we'll move the atoms based on the force acting on Newton's laws of motion. Whereas here, time step is not there, only the cycles will be there. So for all, if you move all the n atoms, then one cycle is completed, then we'll go to the next cycle, and then we'll move randomly. So we'll collect all the configurations. So in both molecular dynamics and Monte Carlo simulation approach, the only basic principle is collection of configurations. We'll move the atoms, and then we'll have n number of configurations. So based on the configurations, atomic configurations, based on the movements of atoms, we'll calculate the properties. We know the temperature, you can calculate the pressure, volume, density, potential energy, kinetic energy in case of molecular dynamics. Monte Carlo simulation, only potential energy we can calculate. And we can know more a lot from these configurations, from the collection of these configurations. Okay, so this is the introduction for both molecular dynamics and Monte Carlo simulations. Okay, one thing I would like to tell is the basic important step here is the force field. Force field means we should know the force acting on the atoms or the potential of the system, potential energy of the system for the movement of an atom. If you move an atom, so we should know the force or the potential acting on it, and that depends on the force field of the system, the development of the force field. Okay, yeah. So we'll apply this both molecular dynamics and Monte Carlo simulations on subatomic particle simulations, and we'll see how it behaves. Okay, now let's go into the main session of this research study. So we all know that Coulomb potentials is a main important role in play an important role in modeling electrostatic interactions between how a proton and electron attract each other, whereas proton repel each other because of the same charge. And the same Coulomb potentials we apply in molecular dynamics and Monte Carlo simulations. Okay. In molecular simulations also, in atoms also carry charges. So we'll apply the Coulomb potentials in it. Okay. At atomic scale, okay, I mean to say within the atom, where electrons are distributed around the nucleus, the Coulomb potential applies. Okay, but when I applied the Coulomb potentials in it and I ran the molecular dynamics simulation or Monte Carlo simulation, I found that the atom is not stable. Okay, the electron is attracted towards the nucleus because of the Coulomb potentials, and it fall into the nucleus, or it shoots away from the nucleus because of the heavy higher potential values and higher velocities, and the atom is not stable. Okay, so the Coulomb potential doesn't work for the classical approach for both molecular dynamics simulations and Monte Carlo simulations, because of all the electrons are attracted towards the nucleus, because opposite charges are attracted and same charges repel. Okay, so to have a new perspective to run the stable atom simulation, so a new perspective or new potentials are needed for subatomic particles in order to have a electronic distribution around the nucleus. Okay, within the atomic scale, I mean within the atom. Okay. Okay, so in this study we'll have a new perspective on subatomic particles, where the subatomic particles like protons, electrons, and neutrons are treated as conventional particles like atoms or molecules, where it has both attraction and repulsion. Attraction at larger distance, when they are very large apart, when they are at very large distances, they'll have attractive nature for an electron and proton. When they come close together, they have a repulsive nature. Okay, within the atom, I'm talking about within the atom, like atomic scale. And when they come so close, they'll have a repulsive nature. Okay, I'll have a video here. You can watch it here. As you can see, the proton and the electron at the larger distance have attraction forces. When they come together, they have a repulsion force, so they go away. So the same thing happens within the atom also. As the electron attracted towards the nucleus, it comes close to the nucleus, but because of the repulsive nature, it goes away from the nucleus. So in that way, we'll have a stable electron distribution around the nucleus. And the same thing applies for proton instead of proton and proton neutron also. The nuclear forces within the nucleus, I model the nuclear forces as within this new potentials itself. I modeled inside these potentials. Okay, so same nature is implemented for proton and proton neutron also. So this approach, or this perspective, or this potentials or pseudo potentials, you can call it. These are not real. You can call it as pseudo potentials. Gives a stable atom for both molecular dynamics and Monte Carlo simulations. Okay, so that's why I developed this approach, and I made the analysis for few atoms and also molecules, and then we developed this approach because we have a stable atom and we have a classical simulations. Okay. So let's see the hydrogen atom for a simple case, where we have a one proton nucleus at the center, and the electron is distributed around the nucleus, around the proton. Okay, let's see how it as you can see, the electron is distributed revolved around the proton without losing its energy. For infinite time, it revolves around the proton, revolves around the nucleus. As you can see, as it comes close to the nucleus and close to the proton, and then it gets repelled and it goes away, and again it gets pulled back because of the attraction forces. So this run for infinite time. I checked it for a longer time scales, and it has a stable atom. I got a stable hydrogen atom in a classical approach. This is a molecular dynamics simulation, not a Monte Carlo. So this is a molecular dynamic simulations, and we'll have a stable atom, and the electron doesn't lose energy, and it maintains on an orbit, or orbiting around the proton, around the nucleus. Okay. And one more thing is the time step for this molecular dynamic simulation I calculated. Usually for atoms and molecules, molecular dynamic simulation time step will be around femtoseconds. Okay, so but here in subatomic particle simulations, so I started with the dimensionless variables. Okay, I started everything is dimensionless variables. I don't know what the time step is at the beginning, so I just had a dimensionless variables of time, velocity, positions, and everything, force, and everything is potential, and everything is dimensionless variables. I converted into dimensionless variables, and then I ran the simulation. Okay, based on the radius of the atom, we have the experimental values of the radius of the atom. From the radius of the atom, I got the variables for distances like sigma value, epsilon and sigma potential, sigma values, and from that I got calculated the time step, and based on the ionization energies from the experimental value, I calculated the time step, and it was found to be 1.67 attoseconds for each time step, delta t. Okay, so the each time step interval is found to be from the dimensionless variable. I converted to dimension variable, and then I found out to be 1.67 attoseconds. So it is in the range of attoseconds. Whereas for atoms and molecules, the molecular dynamic simulation time step is femtoseconds. Whereas here, it came out as attoseconds. So I immediately searched for the literature review of attoseconds, and I found out that electron dynamics of attosecond studies. It's already people are doing attosecond studies on electron dynamics. Okay, so it has a valid experimental validation as well. Okay. Okay, so these are the potentials I developed, an alternative to Coulomb potentials. For electron and proton, we have to only, for simplicity to begin with, I consider only two terms, both attractive and repulsive terms. Okay, for nucleus, within the nucleus, for proton and neutron interaction, I consider two terms. For electron repulsion and attraction, I'll have also two terms. Here we can see we have two parameters, epsilon and sigma, the potential parameters. And for nuclear forces, to model the nuclear forces, nucleus forces, so I included it in proton and proton electron interaction. Okay, I don't have to exclusively add nuclear forces, strong and weak nuclear forces, and those nuclear forces will be modeled here itself in proton and in this middle equation. Okay, so that inclusive of nuclear forces has made me to have, for proton has both attractive and repulsive terms because of the nuclear forces. So within the atom, like inside of the atom, inside of the nucleus, so the proton and proton has both attractive and repulsive terms. Okay, both attractive forces and repulsive forces. So they come close and then they go away. They come close and then they go away. Like that, it vibrates within the nucleus. So that you can extrapolate or interpolate the nuclear forces from that. From these interactions. Okay, and same way we have the electron repulsions and attractions also. We can calculate from these potentials. So for time being, I'm calling this as a pseudo potentials because I'm not yet modeled for electron interaction, and also the nuclear forces I am not included. So for time being, I'm calling it as a pseudo potentials for subatomic particles, and also an alternative to a Coulomb potential for inside the atom, within the atom. Okay. Okay, now let's see the electron energy changes inside the hydrogen atom. As you can see, the dotted black line is a change in the radius. I represented here in the right side of my the plot in y-axis. Okay, it comes close to the nucleus. The radius is decreased, and then it goes away from the nucleus, and then it repeats the cycle. So it is periodic, and also it repeats the cycle. Okay, and the potential energy When it is away from the nucleus, away from the proton, the potential energy is very high. When it is close to the nucleus, when the electron approaches the proton, the potential energy decreases, which means for core electrons, the potential energy is low. And whereas the kinetic energy, which is represented here in pink line, kinetic energy for valence away from the nucleus is low. When it comes close to the proton, close to the nucleus, the kinetic energy is very high, means the velocity of the electron increases, and then it goes away from, due to the repulsion between the proton and electron within the atom, and then it goes away from the proton. The radius increases and the potential energy also increases, whereas the kinetic energy decreases, and this cycle repeats for infinite time. Here I represented for 150 attoseconds, and the energy values are found out to be in the range of 10 to the power of minus 23 joules. So based on the ionization energies from the experimental value, I calculated back the dimensions of the potential energy and kinetic energies. So this is how the electron revolving around the proton for hydrogen atom looks like, how the energy changes, and along with the radius of the atom of the electron. Okay, now let's see. So far we implemented for one proton and one electron. So let's see how the simulation for subatomic particle simulations, like molecular dynamic simulations, behave for a carbon atom which has 6 electrons. So the 6 electrons is placed randomly at the initial. Okay, and the nucleus here I placed in the center with having protons, 6 protons and 6 neutrons. And let's see how the electron distribution is happening around for a molecular dynamic simulation. As you can see, the valence electrons and the core electrons is maintained its orbits. It's revolving around the nucleus. It has both attraction and repulsion between electrons and between electrons and protons. And as I'm zooming in, you can see the movement of protons and neutrons within the nucleus is also captured because of the new potentials, new pseudo potentials I developed in this study. So the protons and neutrons movement is captured here in the nucleus, and the effect of the movement of proton and neutron is seen in the movement of electrons also, distribution of electrons around the nucleus. Okay, so it's both the nucleus dynamics and also the electron dynamics is captured in this simulation, in this molecular dynamics simulation. I'm calling it as subatomic particle simulations, and that in that it is a molecular dynamics approach. We'll see later in the presentation of how the Monte Carlo simulation will look like. Okay, so we have a stable electronic distribution around the nucleus. The electrons doesn't fall on the nucleus, and it maintains its energy, its potential and kinetic energies for valence and core electrons for infinite time. Okay, it is a stable electronic distribution, and also the effect of nucleus movement on electron movements was captured based on molecular dynamics force acting on the electron. So the force acting on electron depends on the position of proton and neutrons within the nucleus also, and that is included, and it made a next move based on the force acting on each electron and each proton. Yeah, so the energies of electron was studied, and here how it looks. This is the density map, electron density map for a carbon atom for 5000 time steps. The center is the nucleus. We cannot see the protons and neutrons here, and we can see the electron distribution around the nucleus. This is the core electron, and whereas the valence electron. You can see the potential energy for the I plotted the graph for potential and kinetic energy. The x-axis is the number index of the electron. 1 represents the core electron, and 6 is the valence electron. So for potential energy, for core electrons it is lower for core electrons. For valence electrons, the potential energy is higher. Okay, so the core electrons are more stable, which means having less minimum potential energy. For valence electrons, it is very high because of unstable, more likely like unstable. Whereas the kinetic energy is reverse. Kinetic energy for the core electrons are very high, means the velocity for the core electrons is high near to the nucleus. When it comes to the valence electron, around 6, the kinetic energy is decreased. So which means that the core electrons, the electrons are revolving very fast. Okay, kinetic energy is very high, and when it comes to the valence electrons, the kinetic energy is low, means the velocities are very low when compared to the core electrons, and the opposite trend is true for potential energies. So this is how the analysis is made for molecular dynamic simulation implemented on subatomic particles using the pseudo potentials developed in this study. Okay, now to see the limits and advantages of this approach, this classical approach on subatomic particles, I implemented it for uranium atom for 92 electrons and 92 protons and 146 neutrons. I placed in the simulation box, and I ran the molecular dynamic simulations and see whether it is the system, whether the atom is stable or not, or right, the electrons distribution, how it behaves. Okay, let's see here. As you can see, the 92 electrons are distributed nicely around the nucleus, and the nucleus is stable, and the electrons, the protons and neutrons are stable. You can see, I can able to capture this simulation, or this approach can capture the protons and neutrons movements and the effect on electron distribution. So the atom is stable and the energies are maintained, electron energies and proton and neutron energies are maintained stable around the simulation for infinite time. Initially the nucleus size is very big because of the initial configuration. As the simulation proceeds, the nucleus size got reduced and a small nuclear size is formed, and the atom got stable in the first attempt. This is in the first attempt itself, I got the stable uranium atom. I got the stable uranium atom in the first attempt. Okay, now let's see the molecular dynamic simulation on the oxygen molecule. So I'm not yet modeled this. I just run a trial simulation on this, and we'll see. So here is the one oxygen atom, and here is another oxygen atom, and we'll have 8 electrons distributed, placed around the nucleus, around here, and also 8 electrons here, and see how the electron distribution happens between 2 oxygen atoms. As we know, the oxygen atom share a covalent bond. 2 valence electrons are shared between each other. So we'll see how it will. So as you can see, the core electrons are revolving around the nucleus of 2 oxygen atom, whereas the valence electron is shared. One valence electron goes to this oxygen molecule, this oxygen atom, and the same way another valence electron is shared between these 2 oxygen atom, another oxygen atom. I'm showing here the nucleus movement also, proton and neutron movement also. So the two oxygen atom has both attraction and repulsion forces acting on it. So the effect of movement of proton and neutron of this oxygen atom on the next another oxygen atom is also captured. Say for example, the nucleus movement of proton and neutron of this oxygen atom was captured on effect on this electron was captured here, and also the movement of proton and neutron of this oxygen atom on the other electron of another oxygen atom is also captured here. So when the oxygen atom has 8 noble gas configuration for each oxygen atom, the potential goes to minimum. Okay, it got inert noble gas behavior. So that effect is not included right now. It will be included in the future studies. Right now it's just a trial of molecular dynamic simulation on using the pseudo potentials developed in this study. Okay. So this is for molecules. Okay, so now this is for a 2 hydrogen atom. one hydrogen atom here, another hydrogen atom here. Each electron, two electrons, one is shared between two hydrogen atoms. As you can see, the electron density is very high in between the two hydrogen atoms. Okay. So as I said, the noble gas configuration like 2, 8, 8, 18 and 32 electronic configurations. If an atom has these electrons around the nucleus, that atom will be inert. Okay, that atom shows inert behavior. So that potential goes minimum. Okay, so I have to include that in the pseudo potentials developed in the study. Okay, not yet included. I will be do it in my future studies. People can see that. And okay, let's move to Monte Carlo simulation. As I said, in Monte Carlo simulation, we'll place within the simulation box, we'll place randomly the protons, neutrons and electrons. For a carbon atom, we'll have 6 electrons. So this green circle is electrons and the orange circle is protons and neutrons. So we'll have 6 electrons and 6 protons and 6 neutrons. As I run the Monte Carlo simulation, I can observe the formation of atom. In other words, all the protons and neutrons came together and form a stable nucleus, whereas the electrons are distributed around the nucleus. Okay, so the atom formation was observed within 500 in the first 500 Monte Carlo cycles. Okay, the next from there on, I collected the electron distribution configurations of the atom for analysis. So the acceptance ratio I used in this subatomic particle simulation is exponential of a difference in energies with the denominator of a tuning parameter C, which is related to the temperature of an atom. Okay, so right now I don't know the value of C. So based on the trial and error method, why we consider the wide ranges of C value tuning parameter, and at each cases the total potential of the atom was found to be constant. Means the equilibrated value atom potential configurations was found to be constant, and to have a reasonable acceptance moves for each trial move, in order to have a reasonable acceptance criteria, the value of 500 is chosen to have a nice samples of trial moves. Okay, here is the simulation video I'll play. So at each trial move, say for example this electron, so this is the nucleus of protons and neutrons is there, and 6 electrons is distributed in a carbon atom. Say for example this electron is chosen and a trial move is made, but the acceptance moves are very low, the sampling is very poor because of, so to enhance the sampling, what we did was we moved the same electron within maintaining the same radius around the nucleus in a 3D sphere, around the sphere of as you can see here in the 2D in the form of circle, the rotated circle. So each electron is moved along the radius of the nucleus. Okay, so for each trial move we consider 10,000 additional samplings to enhance the sampling to have the acceptance criteria. And after implementing this enhancing enhancing the sampling method, we got the electron configuration around the nucleus is very good, and you can see here in the simulation video. As you can see, at the initial itself, the protons and neutrons are randomly distributed in the box. Within the 500 Monte Carlo cycles, the nucleus formation happen, and the electrons are nicely distributed around the nucleus. These are all the random moves. As you can see, you can count 6 electrons all the time. If you run it, it seems like a lot of electrons, but actually only 6 electrons are there. These are the random distribution. So if one can ask, if it is a Monte Carlo molecular dynamics simulation, you are using Newton laws of motion, so that does not apply for electrons and protons and neutrons, because those are the subatomic realm. But in Monte Carlo simulation, I can this argument does not valid, because we are making a random moves. We are not using any Newton laws for subatomic particles. So Monte Carlo simulations at least valid for in this study. Okay, so at each time random move is made on for 6 electron, and then the potential is calculated, and based on the acceptance criteria we accept or reject the move. Okay, so you can say this is not even a classical approach. Okay, this Monte Carlo simulation is not even a classic. You can say this is a quantum approach also, because I'm not having any classical equations used here. Okay, I'm just making a trial move. It can be a quantum move also. Okay, so yeah. So as these are the potential energy plot, and the plot looks similar to the Monte Carlo simulations for conventional atoms and molecules, where it starts with the high potential energy and it comes to the equilibrium state within the less than 500 Monte Carlo cycles. So atom formation has happened by reducing the potential of the whole atom. So the potential energy of the atom decreases tremendously within the 500 Monte Carlo cycles. So the atom formation happened here in this zone, and the rest of the cycles I collected for the equilibration of the atom was proceeded for the next 2000 Monte Carlo cycles. So this is the radius of the carbon atom, and it has a random profile, randomly changed across the Monte Carlo cycles. And the radius of the carbon atom is found to be around 40 pm. So okay, now we saw the molecular dynamics approach, Monte Carlo simulation approach for carbon atom, uranium atom, and hydrogen atom. Now I made an attempt to implement a pilot wave theory. So now that we have electrons can rotate without losing its energy around the nucleus in a classical approach, or also in quantum approach in Monte Carlo simulations. So why not try the pilot wave theory? So why not to have waves, and the electron moves according to the interference pattern in the Higgs field or ether medium. Okay, so here is a simple case where we have hydrogen atom, where the proton is situated in the center. It has a Higgs field or ether medium waves, and the electron is distributed around the nucleus, around the proton, and the movement of electron is based on the interference pattern of these waves of proton and electron. Okay, this is for a simple case. Whereas for a multi-electron system, say for example 2 electrons and a nucleus with protons and neutrons here. So for protons and neutrons we have a wave, and this is red dot is of the electron. So for electron also, presence of electrons is also represented in the form of a wave, and this electron is represented in another wave. So these 2 electrons revolve around the nucleus without losing its energy constantly. So, and this movement is affected by the interference pattern between the collision between the 2 waves. Okay, and I captured this based on the collision mechanism, and the velocity and the acceleration is changed according to the collision between this wave and this wave, and also this wave. Okay, so the movement of electron is not normal. It got disturbed or it got changed because of the interference pattern between these 3 waves. Okay, so this is the simulation for a hydrogen atom, particle wave nature. As you can see, I changed the amplitude of this wave, of this proton, presence of proton waves due to presence of proton. By increasing the amplitude, I can see the radius of the atom got increased, and the periodic nature of orbits of electron got changed. The wavelength got increased. Okay, so based on the presence of wave nature, the distribution of electron around the nucleus is changed. Okay, so that in this study I want to make this observation by the nature of the wave, presence of waves, and also its properties like wavelength and amplitude, the distribution of electrons and the repeating pattern of the radius of atom, and also the distribution of electrons around the nucleus changed very dependent on the properties of the waves. Similar is the case for the carbon atom. I applied for the carbon atom. The same thing happened by changing the electron wave amplitude, electron to electron wave amplitude, and also proton electron wave amplitude. The radius of the atom of a carbon atom changed very sensitive to the changes in wave amplitudes, and it is in the random base. It is not, this does not follow a particular trend, and I need to study more for that. For time being, I just reported in the study. In the future studies, we can model this, and we can get a trend and also an analysis based on this wave amplitude and wavelength of these waves. Okay, so now we conclude the session, and before concluding the this study, let's see the applications of this approach. Okay, so the main fundamental application is we don't need require a force field for any system. If you come up with any molecule, any atom in the periodic table, we just need a force field for a proton, neutron, and electron, which we developed in this study, and also people will come up with other potentials also. So we don't need the force field for each system. Okay, and a universal force field is enough, and also we can simulate any system, okay, for molecular dynamics and Monte Carlo simulations also. Okay, and also we can develop the softwares like Gaussian software, like Monte Carlo molecular dynamics packages can also be created for subatomic particle simulations, as just shown here in this study. I developed it in Fortran for Monte Carlo simulation and molecular dynamics simulation for carbon atom, uranium atom, and hydrogen atom. We can generalize this, and we can develop a code package for this. And also another application we can have is we can model the nuclear waste management. As you can see, nuclear reactors, we can extract the energy from nucleus and nuclear energy from the nuclear reactors, but the nuclear waste is very huge, and we don't know what to do, how to clear it, and how to recycle the nuclear waste. So we can model that simulation. We can simulate that system as well. We don't need a force field. We can just put the percentage concentrations of uranium atom and the water molecules and all those stuff, and we can simulate, and we can see what is happening over there and how to manage that nuclear waste. And also we can use this in drug delivery systems, in medical biological systems as well, and also in material science for property estimation for materials as well. And we can simulate any industrial solvent. We can just put those atoms, and also if you know the formula of that, we can go for the simulation for either molecular dynamics or Monte Carlo simulations as well. We can use the quantum computing or quantum communications systems as well. We can model it. So these are the applications, a few applications I mentioned for this approach. Okay, now we'll conclude the session. This study where we can able to implement a subatomic particle simulation. We can have a classical approach for molecular dynamic simulation, and quantum and classical approach for Monte Carlo simulations. Okay, for Monte Carlo simulations, you cannot say it is a classical approach, because Monte Carlo we just made a random moves. We cannot say it is a classical approach. We just made the random moves of electrons, and we just collected the configuration. It can be a quantum move also. Okay, it can be a quantum move or a classical move for a Monte Carlo simulation. So with this the electron does not lose the energy, and it revolves around the nucleus for infinite time with these new potentials I developed in this study. This is an alternative to Coulomb potentials. Okay. If I implement a Coulomb potential, the atom is not stable. So I search for an alternative for Coulomb potentials. So I developed this new potentials, pseudo potentials, and I have to model this for further based on the nuclear size and the electron distribution as well. So far it is not parameterized based on the nuclear size, and also the electron repulsion, and also the atomic orbitals based on the atomic orbitals that we already have. P orbitals, S orbital, P and D orbitals we have around the nucleus. So we have to model these pseudo potentials or these new potentials based on those as well. That we will consider as a future studies. And also we like to include inert gas configurations. Say for example, for oxygen molecule, we saw in this presentation that between the two oxygen atom, when the oxygen atom has a noble gas configuration, it should have a inert behavior. So that configuration, like this is the ionic gas noble gas configurations, these numbers has to be included in the potentials as well. Okay, subatomic particle potentials, to have the molecular dynamics and Monte Carlo simulations for molecules. And based on these approaches, the new atomic models can also emerge based on the classical approaches for molecular dynamic simulations, and also quantum and classical approach for Monte Carlo simulations as well. New atomic models will come because the electron does not lose energy. Electron does not lose energy, and it revolves around the nucleus for infinite time based on these pseudo potentials. Okay, so a new atomic models can also can come in the future as well. Only 2 terms were included in the potentials as I shown in the slides. So more terms will be considered to have a complex electronic configurations or to imitate the p orbitals, s orbitals, p orbitals and d orbitals, to get the orbital shapes of electron distribution around the nucleus. So more terms will be included, can be considered to have complex electron trajectories or electronic orbitals around the nucleus. And also another direction we need to be considered in the future is the development of particle wave nature. Okay, so far we have implemented particle nature very successfully, and also we had a trial move of pilot wave theory. We didn't model it parameterized based on this, so we have to develop this particle wave nature for subatomic particles as well, for to have a stable atom and also a complex electronic trajectories as well. Okay, so before ending this session, I would like to have an acknowledgement for few people. I'd like to thank Gomati, Koti and Ganesh, Dr. Ganesh, for their financial support on this research. Okay, and I'd like to thank Dr. Subhash Patri for his guidance in this project. At each stage, I got a guidance from him, and how to develop and how to implement and take it to the next level. I got a lot of guidance from Dr. Subhash Patri. And part of the hydrogen atom calculations that I shown in this presentation was carried out during my PhD using Mississippi State University computer. I did my PhD in Mississippi State University. I did part of the hydrogen atom calculations using Mississippi State University computer, and I like to thank Mississippi State University for providing the facility. And at last, I would like to thank my PhD advisor, Dr. Neeraj Roy, for his valuable discussion with me on Lennard-Jones potentials, molecular dynamic simulations, Monte Carlo simulations, how to develop for new systems and all those stuff. I'd like to thank my PhD advisor, Dr. Neeraj Roy. Thank you so much for your time. And here are the references for this research study got published recently in Innovative Journal of Applied Science. It also got preprint which has a DOI. You can go through. I'll provide the link in the description box. You can go through the paper. You can implement in your studies if it is helpful. Thank you so much, and I'll see you again in my future projects. Thank you. Please share this, and if anybody is interested in physics and chemistry related areas. Thank you so much.